Okay.
Hello everybody, welcome to our seminar. I am glad to introduce you to our speaker, Edgar Ventosa. Okay, we wanted to have it here in person, but due to the COVID situation, it was not possible, and we hope that soon he could visit us here at BC Materials. Dr. Edgar Ventosa got his PhD degree in chemistry at the University of Burgos in the field of electrochemistry and nanoscience. He was working as a senior scientist in Germany and also in Spain, and very recently he returned to the University of Burgos. He was involved in many national and international projects, being principal investigator in several of them, such as the project H2020 Nanobat. He was also received prestigious awards in recognition of his excellent work, such as the Talent Program and Ramon y Cajal Award. And Edgar, when you want, you can start with your seminar, name out-of-the-box battery concept, okay?
Okay, thank you very much, Raquel, not only for the introduction, but also for organizing this together with Javier del Campo, this webinar, and giving me the opportunity to showcase some of our recent progress on unconventional battery concepts. So good morning, everyone. This is the outline for today's presentation. So after a short introduction, I will discuss in the section 2 some unconventional approaches that we've been working on recently for flow batteries. In the section 3, I will discuss some also unconventional approach, but in this case for static batteries, and I will finish with a few take-home messages. So there are several ways of classifying a battery. One of them is according to whether the energy storage material or the active material is flowing or is static. In a redox flow battery, the active species, so the material which is actually storing the energy, is dissolved in an electrolyte, which is stored in external tanks, external reservoirs. This electrolyte is pumped into an electrochemical reactor in which the energy conversion takes place. Then the electrolyte returns to the external reservoirs where the electrolyte is stored. The main advantage of redox flow battery is that energy and power are completely decoupled. That means that energy depends on the size of the tanks, while the power depends on the size of the reactor. So basically, if we want to increase the energy but keeping the same power, we just make the tanks bigger. Also, we have direct access to the active material, so it's very easy to substitute them or heal some chemical degradation. On the other hand, we have the static or non-flow batteries, in which the active species are solid particles. The main advantage is that solid particles are able to store more charge, more energy per volume unit, because the higher concentration of electroactive species. So basically, static batteries usually has much higher energy density. Since we don't have a flow, the engineering and maintenance is much simpler. As you can see, each of these two types of batteries has intrinsic advantages and disadvantages. So basically, what we are aiming is to propose new battery concepts which are somehow featuring the best features of each of these two types of battery. This slide basically shows the same message as before, but just with some examples. On the left side, we have the key performance indicators, so sustainability, cycle life, recyclability, etc. For the two state-of-the-art non-flow batteries, so sodium-ion and lithium-ion, and also for the state-of-the-art flow batteries, so all vanadium and zinc bromide flow battery. I'm not gonna discuss in detail this figure, but basically you can see that each of these technologies has green and red. So red obviously means bad, So it has many red key performance indicator, and it's difficult to basically come up with a well-balanced battery by an incremental approach. So basically what we're proposing is to somehow merge these two concepts and come up with new battery concepts which shows a good balance among all the key performance indicators. So my first example is going to be focused on redox flow batteries. The state-of-the-art redox flow battery is the all vanadium redox flow battery. This technology actually works quite okay. The main problem is that this battery is based on vanadium species. So all the all the electroactive species in the positive and negative side are based on vanadium. As you can see here in this graph, the price of vanadium is very volatile because somehow it's located in few countries, and that makes this material a strategic material for the US and the EU. So basically, we need new alternatives, and making a redox flow battery based on organic and organometallic species based on earth abundant elements is a very interesting and attractive approach to replace the vanadium. I think here is basically shows the same, the evolution of the cost of vanadium in recent years. And actually I experienced this spike, as you can see, in around 2018. There was a rapid increase in the cost of vanadium. So basically increased by, let's say, 4 times in less than 1 year. So you can understand that our industrial partners were very nervous at this point, and they were very keen to look for alternatives to vanadium. So alkaline redox flow batteries are of special interest from a practical point of view because of the less corrosive feature of alkaline media compared to acidic or even neutral. So in any battery we have a negative side and a positive side. Here the negative side is represented in blue and the positive side is represented in yellow. So in alkaline redox flow battery we have several promising organic species for the negative compartment, but unfortunately we have only one species which actually works for the positive electrode, which is the ferrocyanide. The solubility is relatively low, which limits the energy density of this family of redox flow batteries. So to illustrate this, I show you here in this graph the volume for the positive and the negative compartment for 3 relevant works. So in the first one, they use anthraquinone and ferrocyanide for the negative and positive compartment respectively. And you can see the volume of the ferrocyanide is 4 times larger than the anthraquinone. Now, in the next work, the energy density, so the volume of the tanks were reduced, but still the volume of the positive side is between 4 and 5 times larger than the negative side. Yeah, progress has been made, but the same problem still. As I mentioned, the volume of the positive compartment is much larger than the negative side. So basically this means that if we want to address the issue of the low energy density in alkaline redox flow battery, we need to address the positive compartment, not the negative compartment. As I mentioned, the solubility of ferrocyanide is the problem. It's around 0.4 molar in 1 molar KOH, which means that give us 10 ampere hour per liter. On the other side, solid particles are able to store more charge per volume unit, as I mentioned before. For instance, nickel hydroxide, which is used for nickel metal hydride batteries, is able to store 2 orders of magnitude more charge per volume. So the question is, why don't we just use solid particles in a redox flow battery? So by definition, the electroactive species of the energy storing material is stored in external reservoir. So basically that means we will need to confine our solid material in external reservoir. This external reservoir is centimeters or even meters away from our electrochemical reactor. That would mean that there will be no electrical connection. There will be no way to charge and discharge these solid particles. So this is the conventional belief, let's say. So in our approach, instead of using ferrocyanide as an active species, we use it as a molecular wire to store energy, so to transfer, let's say, the charge between the electrochemical or from the electrochemical reactor to the solid particles which are confined in the external reservoir. So basically, this is a scheme of what we are proposing. These are the ferrocene and ferrocene species. So let's call it iron 2 and iron 3 for simplicity. So basically, we pump iron 2 into the electrochemical reactor. The iron 2 is oxidized to iron 3. So basically, it's delivering one electron to the current collector. Now the iron 3 goes back to the external reservoir. And now here what we need to happen is that the iron 3 is reduced to iron 2 and is taking one electron from the nickel 2, which gets oxidized to nickel 3. So in this way, we regenerate the iron 2, which is pumped back to the electrochemical reactor. So basically, the iron 2, iron 3 is just the molecular wire, and we store the charges actually in the solid particles. Okay, so for this concept to work, we need a spontaneous and reversible reaction between our redox mediator and the solid particles. Here it gets a little bit probably too technical, but I need you to believe that there is a thermodynamic reason. There is no black magic involved, let's say, in this concept. So it's basically possible, and it will take me 2-3 minutes, okay, to explain this. So basically, in an electrochemical reaction, there is always something that gets oxidized and something that gets reduced. So if the redox potential of the reduction reaction is above the redox potential of the oxidation, this reaction will take place spontaneously from a thermodynamic point of view. I think the best example is the Daniel cell. So basically, we have copper 2 and we have zinc 0. So if we put them together, they will react because the redox potential of copper, which is actually the reaction that is going to get reduced, is above the potential of the zinc, which is going to get oxidized. So this reaction is taking place spontaneous. Okay, so now we look at our system, and this figure represents the evolution of the redox potential of our solid particles as a function of the state of charge. This is not actual data. This is just a drawing for explaining the mechanism. Okay, so basically, in our system, we will need one species for the charging, and the redox potential of this species will need to be above the redox potential of the solid. So I call it the species A to species A+. So the A+ will react with the nickel 2. So the A+ will get reduced to A, and nickel 2 will get oxidized to nickel 3. So this will happen during the charging process. For the discharging, we need a redox mediator, which redox potential is below the redox potential of the solid particle. So basically, we will be reducing B+ to B0, and this B0 will react spontaneously with the nickel 3. Nickel 3 will get reduced to nickel 2, and we will regenerate the B+. So basically, what I try to transmit here is that we need two pairs of redox mediator, one above the redox potential for charging, one below the redox potential of the solid for the discharging process. Fortunately for us, the redox potential of dissolved species actually evolved significantly with the state of charge following the Nernst equation. That means that if we are lucky and we found the right conditions, which will be these conditions here, in which the redox potential of the two, so dissolved species and solid particle are crossing around 50% of your charge, this reaction will be spontaneous using only one redox mediator. So basically what will happen is we start somewhere here, this red point here, and then we will be charging our battery, redox flow battery, and the redox potential of the electrolyte will be changing, will be increasing with the state of charge, and there will be a point where actually the redox potential of the electrolyte is above the redox potential of the solid. From that point on, our electrolyte will become a redox mediator for the charging process. When the charging process is complete, then we will start the discharging process, and we will start at this point here. The redox potential of the dissolved species, the electrolyte, will decrease. As we decrease the state of charge, it will reach a point where the redox potential of the electrolyte is below the redox potential of the solid particles. From that point on, our mediator will become, our electrolyte will become a redox mediator for the discharge. So basically, thermodynamically, it is possible that just one single redox species is acting as a redox mediator for charging and discharging. So that's the technical part is over. Now we go for a more intuitive demonstration. So we took nickel hydroxide, which is green. We put in filter paper, and then we add iron 3. There are mistake here. This 3 glass, so it's iron 3. And as soon as we add the iron 3, the solid become black. That means that actually we are oxidizing the nickel 2 to nickel 3. But the nice thing is that when we add nickel 2 on top of the when we add iron 2 on top of the nickel 3, then the nickel get reduced back to nickel 2. So this exactly is the same, but in this experiment what we did is we generate the iron 2 and iron 3 electrochemically. So it's just the same example. And so we see that we are able to oxidize and reduce the solid particles with the electrolyte. Now we want to quantify how much of this solid particle is available for storing energy. So we set up, or we assembled this what we call a symmetrical cell. Symmetrical because we are using iron 3 in the positive compartment and iron 2 in the negative compartment. So the cell voltage is going to be 0, so it's not a battery. But if we oversize one of the compartments, so for instance the iron 3, we make it very, very big. So the electrochemical response will be limited by the iron 2. So basically we will be able to monitor what's happening in this compartment. So initially we don't have any nickel. So it's this point here. The capacity is limited again by this compartment here. And we can calculate, we can estimate the theoretical capacity of this compartment here. And it's a value here, I don't remember, maybe 8 ampere hour per liter. So basically we get a value which is very close to the theoretical value. Then we add some nickel into this limiting reservoir. And the capacity exceeds the theoretical capacity. So basically meaning that we are storing energy in these solid particles. And the more nickel we add, basically here it represents amount of nickel per volume of electrolyte. So it means that we are increasing the amount of nickel, then we get more charge. And from here, we actually determine that we are able to use around 40% of the theoretical capacity of this solid material. We also tested the cyclability. Here is the Coulombic efficiency is close to 100, and the capacity retention. So that means the ability to retain this capacity with cycling is rather good. Actually, there is a small fading, but this is due to the oxygen evolution and the unbalancing of the cell, not due to the let's say decomposition or some failure in our storage mechanism. So then we implemented this concept into a full, let's say full alkaline flow battery. We actually implemented in several chemistries, and I'm focusing here on the phenacene ferrocyanide. So basically, we assemble a battery in which we oversize the positive compartment. So we make this compartment very big. So basically, let's say the performance of this system is gonna be limited by the negative side because it's very small. So we know the concentration and the volume of the phenacene, so we know the theoretical capacity, and actually this is the voltage profile of the battery. And I don't remember exactly, but maybe it was supposed to give us 120 milliampere hour, and we get something very close to the theoretical capacity of this phenacene. Now, what we did is this cell, we reduce the volume of the positive compartment, and actually we make it even smaller than the negative. So now the limiting side is the positive compartment. So basically the capacity decreases from here to here. I think the theoretical capacity of this compartment is something around 80 milliampere hour, and we get 75. So it's pretty clear that the ferrocyanide is limiting the performance of the system. Okay, so now in this very same system, we just added some particles, nickel particles, and we confine them into the external tank, and this is the green. So basically, the capacity increases, and it's interesting because now the negative side becomes the limiting side, although the volume of the positive is very small. So basically, the nickel particle, a small or little amount of nickel particle, is compensating a large volume of ferrocyanide. Another way of showing this is basically the evolution of the capacity with the number of cycles. So basically, we assemble a battery without any nickel hydroxide, and basically the capacity is in the first cycles here. You can see here is around 80 milliampere hour gram. Then during cycling, we just add nickel into the system, and the capacity just jump here and at around 130 milliampere hour. There was a small decay, but as I mentioned, is because of the unbalancing. We actually implemented a procedure that we developed to, let's say, compensate the system, and we see that actually is stable for 200 or 100 cycles in this case. Basically, when we represent the values that we obtain with the state of the art, we saw that these are very relevant, let's say, relevant works, and actually our energy density somehow here is actually more than 2 times the value that it was previously reported. So it's it seems like an interesting approach to follow. In the third section, I'm gonna discuss another unconventional approach, but in this case for non-flow batteries or static batteries. This graph shows the battery factory capacities, the evolution of the battery factory capacity within the next years. Basically, this represents the amount of battery that are gonna be produced per year, and we see here that in 8 years, it's estimated that we are gonna produce around 7 million tons of batteries a year. So that means that we need to recycle those batteries. Right now, we only recycle around 5% of lithium batteries, and this is the, let's say, the scheme of linear economy for batteries. Basically, it all starts with the mining of the elements. Here I differentiate between active material, so the material which is actually storing the energy, and the inactive material that will be current collector, separator, gaskets, etc. Okay, so basically we mine, for instance, lithium and cobalt, and here in the material production, we produce the lithium cobalt oxide, which is our active material. Here we mine copper, and we make here copper foils for current collectors. So we produce our battery, we use the battery and dispose. We need to make this circular, And this is basically the scheme of a circular economy for lithium battery. And basically the problem is that these steps here for the recycling are very expensive, and that's the reason why we don't recycle nowadays. So the main problem is that the active material is fixed inside a sealed cell. So that means that we need to crash, we need to destroy the battery to access and recover this active material. When we crash, in contrast to lead acid, in which basically all the elements are lead, and this is very easy to recover, in other type of batteries, we have many elements. So we crash the battery, and then we need to separate different elements, and then we recover these elements through a hydrometallurgic process. So basically, the problem is that the active material is fixed inside the electrochemical cell. So we propose that we pre-assemble electrochemical cell, and then we fill this electrochemical cell with semi-solid electrode. A semi-solid electrode is a dense slurry containing the carbon additive, the active material, and the electrolyte. It's very dense, but it's still flowable. So that means that we can actually inject the active material into our cell. So basically, we actually make our battery, then we seal the battery, we use the battery as usual, and when it reaches the end of life, we have the possibility of de-injecting or removing this semi-solid electrode. And then the cell is ready for being refilled again. Okay, so this is the scheme of the circular economy. So when we plot here our approach, that will mean that we extract the semi-solid electrode, the cathode and the anode, so the positive and the negative separately, and we don't destroy the cell. So that means we don't need to separate the current collector, the membrane, and all these elements. So let's say we simplify a lot this separation, and most importantly, we reduce the entire cell. So that means that because we don't destroy it, we don't need this blue line here of, let's say, recovery of inactive material, so current collectors and separators. So we don't destroy it, we don't need to recover it. So we just reuse it directly. For the proof of concept, we choose the aqueous zinc lithium iron phosphate battery for two reasons. Aqueous is easier for building a prototype, and the zinc lithium iron phosphate chemistry suffer from poor cyclability. So that means that we don't need to wait for too long for the battery to die and then to recycle and demonstrate our concept. So basically, we built our battery. It contains a zinc foil, our porous separator. Then we so with a gasket, we define a space which will be filled with the semi-solid, and we actually fabricated by 3D printing end plate. So we injected the semi-solid electrode, which contains the lithium iron phosphate carbon additive and electrolyte. We use this battery until it dies, basically, and then we just remove the dead electrolyte, that dead electrode, just with tap water, and basically, actually, we recover directly the spent, as that's how we call it, the spent electrode, and the cell is ready for a new injection. So this is the voltage profile of our prototype in the, let's say, as fabricated. This is the first cycle, charge and discharge. Basically, the values are pretty good. So we get 130 milliamp per hour gram of LFP, which is a very good value. And after 50 cycles, the battery has failed, basically. And this is now it's time to recycle or regenerate this battery, and in blue, this is the voltage profile of our regenerated battery. The values are pretty similar, especially for the discharge, which is the important one. We see that after 50 cycles, capacity has faded a lot. So after 50 cycles, we regenerate it again, second regeneration in green, and again and again. So basically with this, we show that it is possible to regenerate our injectable battery, and basically the performance of the regenerated battery doesn't get any worse than the initial one. But now one could actually wonder if the poor cyclability is an intrinsic issue with the semi-solid electrodes of the injectable battery, or it's just because of the chemistry, as I mentioned. So basically, we investigated several approaches. We have here the evolution of the capacity retention with the number of cycles for 3 different chemistries. So in the first, in green, basically what we did is, instead of using standard electrolyte, we use a super concentrated electrolyte. That means that we increase the concentration of salt from 1 molar to 20 molar. In those conditions, there is no free water, because all the water is forming acting as a cell for the ions. So basically, we mitigate a lot the hydrogen evolution. In blue, basically, we directly replace the zinc, because we know the zinc has many issues and actually trigger pH changes, and LFP is very sensitive to these pH changes. So basically, we just replace the anode, the negative side, by lithium titanium phosphate. And here in red is an interesting approach. So basically, we replace the negative side by iron phosphate. So that means that we make, again, a symmetrical cell. So I think this needs some explanation. Basically, we pre-oxidize lithium iron phosphate and we get iron phosphate. So basically, we inject lithium iron phosphate on one side and iron phosphate on the other. Again, this is not a battery because the cell voltage is 0, but we can evaluate the intrinsic stability, cycle stability of the system, because basically in the positive electrode, we will have the oxidation of lithium iron phosphate to iron phosphate, and in the negative side, we will have the reduction of iron phosphate to lithium iron phosphate. Go back here. So basically, the red shows the intrinsic stability of our lithium iron phosphate semi-solid electrodes, and we get a value of 0.08 percent retention decay per cycle. Actually, when we look into the literature to compare, we saw that actually this value is above the state of the art for aqueous systems. So basically, the semi-solid or the injectable electrode is stable. It's not, so the degradation is as good as in any conventional electrode. We also realized that LFP, or lithium iron phosphate, probably is not the best choice for aqueous system, because it shows a long cycle stability in non-aqueous system, but in aqueous system not so much. Not just in injectable electrode, but in any type of electrode, and seems to be related to the sensitivity to the pH changes and all this. So basically, main message of this figure is that we can improve the cyclability, and probably the LFP is not the best choice for aqueous systems. And finally, we make some estimations in the cost of battery. So basically, this shows the contribution of each component to the overall cost of the battery. These estimations are for the lithium iron phosphate, lithium titanium phosphate, and we see that in red is the inactive material. So that means current collectors, separators, etc. Represent 80% of the overall cost. That means that once we assemble the battery, the second battery, so once we regenerate the battery, it will cost us only 16% of the initial cost. So basically, there is a saving of 80% every time that we regenerate the battery. And since our concept is supposed to be implementable to any battery chemistry in principle, we make a more general estimation of the cost reduction as a function of the cost of the active material. So right now we are somewhere here, but if we find cheaper active materials, so that means that the impact of the injectable battery will be even larger. I don't like long conclusions, so I'm gonna give you just 3 take-home messages. First one is if we want non-incremental improvement in our battery performance, we will probably need to explore unconventional approaches and new battery concepts. So in contrast to, let's say, conventional belief, it is possible to use solid active materials in a redox flow battery by using the dissolved species as a redox wire. And basically this concept that we propose, the injectable battery, facilitate a lot the cyclability. So from the environmental and economical point of view, it's an interesting approach to follow in the following years. Basically, with this, I finish. I would like to thank Teresa Paez and Daniel Perez Antolin, because they are the person who actually perform all these experiments. The financial support, and all of you, for your attention. Thank you.
Thanks a lot, Edgar, for your nice talk. Very, very interesting. And now, if you want, we're going to start with the questions from the attendees. And I'm going to read them to you. We are going to start with the first one. Danny wants to know how much the feasibility of recycled batteries is improved by avoiding shredding and mechanical separation steps.
So I don't know if I get how much flexibility. Again. Flexibility.
No, flexibility. No. I can't.
Feasibility. Okay. So basically, the lithium batteries, they are feasible. So that means that so far, so I don't know if I get the question right. So the lithium battery is feasible because it works, and actually the cycle life is very good and the key performance indicators are good. The problem is the recycling is very expensive. Okay, so we could maybe try to search for more sustainable active materials. So removing cobalt, for instance, from lithium batteries. But I think that we need also to search for new approaches for the recyclability. So yeah, I don't know if I get the question right. I don't know if he can actually reformulate the question.
Okay, Danny, if you can reformulate the question, just to clarify.
How much is it? So basically it means, okay, I don't know if feasibility is, so basically what we do is we not only change the recyclability process, but we actually are changing the fabrication of the battery, because basically means that we are actually reusing the whole cell. So we are not destroying the battery. That means that we are able to reuse it. So if the electrochemical performance of this injectable battery are improved and actually gets as good as other batteries, then it will be, I mean, of course it will be a good option, because it will be much cheaper to recycle the battery, because basically we are just regenerating the battery. We are not recycling the battery. We are regenerating the battery. So that's the thing.
Okay, thank you. The next question is regarding flow batteries. How does affect the flow speed in the performance of the battery?
Okay, so I guess that he's actually, Manuel is asking about the electrolyte solid particles reaction rather than the reaction taking place inside the electrochemical reactor. So basically, of course, it has an influence because we need to, let's say, remove the species that we generate away from the solid particles. But we believe that engineering at this point is even more important. So having a good reactor in which there is a good contact between electrolyte and solid particles is more important. So making a good design is at this point is more important than the flow rate, let's say.
Okay, and regarding the semi-solid, how does affect the temperature, and if it could be proposed to batteries for EV regarding leakage issues?
Okay, so temperature, we didn't test it. In principle, it would be beneficial. So the performance is supposed to be better than conventional batteries, and the reason is they are more porous, the electroporosity. So let's say the volume of electrolyte inside the electrode is higher, so the mass transport inside the electrode is higher. So that means that in low temperatures, the performance is probably going to be better. But for the same reason, because the electroporosity is higher, the energy density is going to be lower. So basically, we did also some estimation about the impact of the electroporosity on energy density. And basically, I think we demonstrated something around 70% electroporosity, keeping in mind that the conventional electrodes are around 45%. We think that this is going to be a big problem, energy density. So we're not going to reach the same energy density as conventional batteries. So basically, our conclusion is that this concept is more interesting, is more attractive for stationary application rather than electric vehicle. So I don't think we're going to see this approach applied for electric vehicles. So it's meant for a stationary energy. Yeah. And leakage issue, they are completely sealed. So I mean, basically what we did is we use our knowledge on redox flow battery and transfer it into this static battery. And basically, since you inject and then you close, let's say the risk of leakage is even lower than in a redox flow battery. And redox flow batteries usually don't leak. I mean, of course, there could be some problems, but in principle, you are supposed to operate the battery in static conditions for many years, and then just apply flow for few minutes or few hours every many years. So no, the leakage is, I'm not so much concerned. I'm concerned about the electroporosity and the lower energy density as compared to conventional solid batteries. Yeah.
Okay, thank you. We have a lot of questions here. Deborah Ruiz wants to know about the reactivity of the nickel hydroxide. How long could it be stable in the reservoir?
That's actually a good question. That's a good question. We didn't actually explore the self-discharge. So I assume that the self-discharge will be similar to any nickel metal hydride battery. So basically, because the redox potential of nickel 3 is above the redox potential of oxidation of water. So basically, all I explained about these technical details, this spontaneous reaction is happening as well between the, let's say, charged nickel and the water. So I don't have an answer. I think this is a point to be explored. So for sure it will not be like a super cap. So I'm expecting values similar, so self-discharge values similar to the nickel metal hydride, because we are operating in similar conditions. Yeah.
Okay, another question is regarding the organic molecules. Is it needed that they are anthraquinone-based compounds?
No. So actually, we implemented the concept for anthraquinone, but we also implemented for phenosine. So basically we focus on organic compounds because our partners were interested, or industrial partners were interested in organic compounds. But we actually also implemented in the zinc iron. So this is a classic battery. Also, it's a hybrid in a hybrid configuration. So basically, we are only flowing the positive compartment. The negative is just zinc in alkaline media. So that means it's less corrosive. And it worked. Actually worked quite well because we don't have this unbalancing. Is less pronounced in alkaline media. So in the case of zinc, so basically it worked quite well in zinc iron as well. So in principle, no, it's not restricted to anthraquinone compounds. No.
Okay, thank you, Edgar. She wants to know if the interface impedance between current collector and slurry electrode become an issue.
That's actually a good question, and we actually had to address this also. There was a question from the referee, and we performed a series of experiments to show that the resistance or the impedance is not bad. Actually, so we implemented also this concept for different chemistries, and the resistance, the internal resistance, is not higher than in a conventional electrode. Let's say that's what we observed. So in principle, I understand the question. Maybe when you apply very high current, let's say very high C rates, it may become, but at moderate C rates, let's say 1C, 2Cs, we didn't observe any additional overpotential.
Okay, perfect. We have a question from Daniel. Can the whole value or production chain of batteries be ensured in the European Union in the near future?
No, so it cannot. So we cannot ensure the. That's actually one of the main concerns from the European Union perspective, and that's why actually promoted or encouraged us to look for approaches which are facilitating this recyclability, because we really need to recycle our batteries, not just for environmental issues, but also for sustainability. I mean, we need elements that are not located in Europe. So for instance, even lithium, just as simple as lithium in a lithium battery, it basically comes mostly from South America. Yeah, we don't have yeah, it's a big concern, the European Union.
Okay, thank you. And I think that we are going to do the last one. Is from Javier. He's suggesting you if you could comment on what you consider the ideal applications for the injectable batteries. That is a very nice approach.
Okay, so ideal application, as I mentioned, I mean, basically I answered probably the question with the previous one. Stationary applications. So basically, cheap chemistries in the sense that, so because the cost of the whole battery is not just the active material. So in a battery we have many components, many elements, and sometimes we neglect the contribution of some elements like the current collectors. But when the chemistry is cheap, let's say zinc manganese oxide is so cheap that the other components are responsible for the high price. So in those cases, this concept is often special interest, and actually we are already working on this zinc manganese oxide because we think is probably the best case. Then another is not really related, so it's related, but not directly to this, is we are trying to expand this approach to other applications like structural batteries, because as I mentioned before, the end plates are 3D printed. So basically it opened up the possibility of printing the electrochemical cell with a 3D printer and filling the battery with a semi-solid. We are already exploring also this possibility.
Okay, thanks a lot for your very nice talk and congratulations for the amazing job.
Thank you. Thank you.
And okay, we finish here. Thanks to all the attendees, and we hope we can start collaborating together.
Thank you. Thank you. Bye. Thank you, everyone.